Wonderful. Hi again. My name is Lauren Taylor, and I'm the Policy and Science Director with the Beaver Institute. I'm very glad that you all are attending our webinar today. Why don't we first start with taking a minute to type into the chat, let us know who you are, where you're coming from, and as you do that, I'll start the introduction for our speaker for this month's series. So we are featuring Dr. Camille McNeely. She's presenting today on our beaver dam analogs and effective restoration techniques in wildfire-impacted semi-arid watersheds. Dr. McNeely is a professor of biology at the Eastern Washington University. Her research encompasses a variety of topics in applied stream ecology with interest in stream restoration, invertebrate biodiversity, and nutrient cycling. Recent projects in her laboratory include evaluating the effectiveness of beaver dam analogs to improve water storage and reduce incision in wildfire-impacted streams, macroinvertebrate distribution and diversity in major watersheds of the inland Northwest USA, and environmental determinants of distributions of freshwater sponges and fairy shrimp in the inland Northwest. So we're excited to have Dr. Camille or McNeely, sorry,
That's quite all right.
speaking
You can call me
today.
Dr. Camille.
And without further ado, I'm going to turn it over to her to guide us in this talk.
Hi. So I'm Camille McNeely, and I am a professor at Eastern Washington University, and I'm going to tell you about some work that we've been doing in collaboration with the Methow Beaver Project, and really want to extend my thanks to Alexa Whipple, who's one of our co-authors, and Joe Wyrick at the Methow Beaver Project. And I also want to highlight my co-authors in this research. So Sawyer Nagel was a master's student here at Eastern, finished in 2024. And I'm going to talk a bit about their thesis data. Caitlin Killoy was also a master's student here at Eastern, and I'm going to talk. She did a lot of the pre-BDA, the before data. This is going to be a before-after control impact study that I'm going to highlight. And then Rebecca Brown is my colleague here at Eastern, and she's a riparian ecologist and a plant ecologist. And so she's really the riparian and plant expert in this project. My slides came up fine. Okay, great. So the area where we've been working is primarily in central Washington in the Methow and Okanagan watersheds, where we are working in 5 tributary streams. And these streams have all been affected by severe wildfire. And in our region, wildfires, extreme wildfires are becoming more common as a result of climate change. And all of these streams burned within 10 years of the study initiation, pretty severe fires. 3 of them were within the area affected by the Carlton Complex fire, which was a major mega fire here in Washington in 2014. And all of them were subsequently experienced increased channel incision as a result of high flow events following those wildfires. So we have that history for these watersheds, and the restoration that I'm going to talk about was in part in response to those wildfire events and subsequent worsening of incision. Almost certainly all of these streams had experienced a long history of incision as a result of grazing and other land use impacts, but it was definitely worsened by fire. So I don't really have to tell this group that beaver can be an important component of recovery of streams, channels from incision, um, as they slow water and allow for aggradation of sediment that has a lot of downstream benefits for stream ecosystems. In our study, we had sites that were beaver sites as well as sites that were planned for BDA restoration and sites that were control sites. And I'll talk a little bit more about that study design, but I just wanted to show you some photographs and some channel profiles. These are on the far left, one of the sites slated for BDA restoration. In the middle is its paired control site. So you can see that both of those sites experience pretty strong incision. If we look at the channel profile and the width to depth ratio. And then finally on the right, this is a paired beaver site. And we can see there's dramatically less incision there as we would expect with beaver activity. So our goal was to examine the effectiveness of beaver dam analogs, so structures that people build to try to mimic some of those ecosystem benefits of beaver in these wildfire impacted incised streams. And I'm going to focus in this talk on water retention and a little bit on sediment retention. So the design of this study is that we had for what I'm going to call the BACI study, which is a before-after control impact study. We had 5 sites for BDA restoration, and each of those was paired with an upstream control site. And we tried to pair these sites with matched beaver sites. And in some cases, we were successful. But as you guys, I'm sure, are all familiar with, beaver move and beaver get trapped. And so we didn't have active beaver in all of the places that we had hoped to monitor them in all years. So we collected data prior to BDA construction for all of the BDA and control sites, as well as some beaver sites. And then we monitored these sites throughout BDA construction. I'm just going to talk about before and after data. And we didn't collect all parameters through the construction period, but we have collected all parameters before and after. And I'm going to focus this talk, and to a large degree, we focused our study on water and sediment retention. And the reason for focusing on water and sediment retention is because, well, one reason is because these are really key to other ecosystem benefits of beaver. So if the BDA restoration wasn't effectively impounding water and trapping sediment, then we don't think we would see increases in groundwater storage, aggradation, and benefits to riparian vegetation, etc. So retention of water and sediment are really, we felt, key to a lot of these other ecosystem effects. This is a figure from a Nash et al. Bioscience paper that came out in 2021. And this is their flow chart of beaver or BDA restoration. And you can see that they've placed water retention and sediment retention right there in the middle as key to these benefits. Water storage is also potentially a direct benefit of beavers or BDAs in terms of providing access to water through dry periods in the summer. So today I'm going to talk probably mostly about water travel time, which is just a way of quantifying velocity of water moving through a stream section, including all the pockets of water, so slow moving water as well as thalweg and higher fast places where the water is moving faster. And I will talk a little bit about sediment retention as well. I'll talk a little bit about some other water retention parameters, but I'll mostly focus on these. I also wanted to mention, before I get too much further, I talked about all of our study sites being affected by wildfire. Another really important piece of context in terms of these study sites was that this study started in a period of extreme drought. So all of our pre-construction data were collected in 2021, which was a very severe drought, as well as the hottest summer on record for the region of our study. And I believe 3 out of the 4 years in which the study took place were drought years, but we definitely started off with the driest conditions in the study in 2021. So this is a graph of pre-restoration data, so prior to any installation of BDAs, and just comparing the topographic conditions for these channels. Whoops. So on the left, we have width-depth ratios, and that's bankful width divided by depth, the thalweg at bankful, for beaver sites on the left, and then control and pre-BDA sites on the right. So we can see there's a lot of overlap between the controlled pre-BDA sites. They're pretty comparable, and we had much wider stream channels at the beaver sites, as we would expect. And this is data for vegetation prior to restoration. And these results are a little bit more complex. We had significantly higher proportion of woody riparian species in the floodplain, for example, in both beaver reaches and control reaches compared to the pre-BDA reaches. And that is probably a combination of these pre-BDA sites were really in need of remediation, of restoration, and the control sites were upstream of them. They were generally quite incised, but they were further upstream in the canyons, and so probably were in a little bit narrower valleys, and that vegetation had a little bit more protection. Similarly, these are data for proportion of wetland species at beaver sites and control and BDA sites, but again, this is all prior to BDA installation. So I want to talk now about some of the hydrologic data that we collected. And for the BDA study, the BACI study, I'm going to be showing data where we basically measured the movement of water through stream reaches with or without BDAs, and in some cases, beaver reaches using a conservative tracer method where we are dripping rhodamine or salt into the stream at a constant rate, and then measuring when those concentrations reach a plateau concentration upstream and downstream of the reach. So these data show the time to travel through a 200-meter reach. This is pre-restoration data that's collected under low flow conditions, so base flow conditions in August and September. And there really was no consistent difference between control reaches and pre-BDA reaches. Those had about a 50-minute to 1 hour span of time to travel through those reaches. And then the time to pass through beaver reaches ranged from about twice as long to 400 times as long. So much, much slower travel times under in reaches with beaver dams, as we would expect. This is a similar graph for high flow conditions. So this is spring snowmelt conditions. Typically, we're seeing about 100 to 1,000 times higher discharge. And as we would expect, travel times are faster, but we are still seeing no consistent difference between control and pre-BDA reaches and significantly slower travel times in reaches with beaver dams. These data show travel times post-restoration, and I'm just showing the BDA and control reaches to keep things simpler, and also because we weren't able to follow all of the BDA reaches throughout that period. I mean, all of the beaver reaches throughout that period. So in this graph, what we have on the y-axis is the change in the travel time. And so this means that if we have a negative value, water is moving through the reach faster than when we collected our pre-restoration data in 2021. And what you can see is the water is moving through these reaches faster almost everywhere because 2021 had very low discharge. So certainly for all of the control reaches, we saw a decrease in travel time. For our BDA reaches, in some cases, we still saw a decrease in travel time. In one case, we saw an increase in travel time, but water was moving significantly more slowly through the BDA reaches compared to the control reaches. So if we look at the change in travel time and we compared that with a paired t-test, we saw significant difference, meaning water wasn't going as much faster through the BDA reaches. In general, the BDA reaches and those BDAs were significantly slowing the water through these reaches. And this is data in the same format for high flow conditions. And we can see that, again, in general, water is traveling faster in post-restoration than it was under extreme drought conditions in this case, the spring of 2022. But we saw actually a slowdown in the movement of water for most of these BDA sites. And this is all data collected 1 year for low flow conditions and 1.5 years for high flow conditions past after the BDAs had been installed. But one thing you'll see in both of these graphs is that these effects were not consistent in every stream. So under low flow conditions in Chilloust Creek, under high flow conditions in Cow Creek, we didn't see that much slowing of water. The BDAs in this study are being maintained. So branches are being added as those branches, disintegrate and lose needles. But that maintenance is pretty infrequent, about once a year. And so where we collected all this data in a fairly short period of time. And so where that fell with respect to that maintenance schedule may have been one of the factors that was part of why we saw these variable effects. Um, I want to talk a little bit about data that my graduate student Sawyer Nagel collected for their thesis. And this is data that's now in review at Restoration Ecology. And this data included some of the same study sites as our Backey study, but it included a wider range of sites. And for that wider range of sites, we don't have before data. So this is going to be looking at beaver dams, BDA restoration sites, and control sites, but doesn't include pre-restoration data. So this is all data at least 1 year after BDAs were installed. This project was able to include BDAs that were established by a variety of organizations. So we're looking at construction of BDAs by more than just one restoration practitioner. So in this data, in addition to looking at travel time, this data is also going to include hydraulic residence time, which is basically how long it takes for the water in an impoundment to be replaced on average. And we're also going to look simply at impoundment volume. Sawyer looked at dam dimensions as a potential predictor of these water retention characteristics and also porosity as determined visually through high resolution photos of the dams for BDA structures. And so in this data set, which again doesn't include before data, but includes a larger geographic range and a greater set of restoration practitioners, we again found that BDA structures control or slowed water compared to control reaches. And in this case, on average, water velocity was about twice as fast in the control reaches, or we could say the BDA structures slowed flow about twice. So water was moving about 2 times more slowly through BDA reaches than control reaches. Comparing hydraulic residence time, so how long water remained in impoundments between BDA structures and beaver impoundments, we found a much, much bigger effect. Rather than water moving about twice as slowly, here water is moving about 1,000 times more slowly. So these, on average, there was a lot of variability, but water was remaining in the beaver impoundments for about 1,000 times as long as it was remaining in the BDA impoundments. So seeing a difference between BDA impoundments and control reaches, But we are also seeing nowhere near the magnitude of effect for these BDA structures that we observed for beaver structures. And we found a really similar difference then between the BDA structures and the beaver structures for pool volume. And that's just the amount of water that is being held in those impoundments. So Sawyer also looked at dam construction parameters and so found a significant effect of height of the dam. So taller dams held more water. And this was true even when we controlled for discharge. Thicker dams held more water. And you can see here that in general, beaver dams were thicker than BDAs. So this is potentially a good target for adapting BDA construction methods so they can retain water more effectively. Porosity, we have porosity data only for the BDAs, but not surprisingly, residence time was strongly affected by porosity, where you can see both of those are log scales, so porosity had a pretty substantial effect on how fast the water, how well the BDA structures were retaining water. And in some cases, in some ways, this is a pretty obvious result that a structure with fewer holes would retain water better. But we actually, in talking before and during the study with the practitioners who installed a lot of these BDA structures, they were not oblivious to the importance of porosity, but it was one of the obstacles to making the structures less porous was permitting. And it was much more difficult to get permits that would allow them to move sediment to fill in these structures and reduce porosity compared to the permitting needed to build the structure at all. So I'll talk briefly about sediment retention. And ultimately, we plan to look at sediment retention through both looking at sediment composition and also looking at bed level changes. But I'm only going to talk about sediment composition data today. So we do have channel profiles for all of our sites post-restoration, but we are still in the process of analyzing that data. And in fact, I still haven't received all of that data from Joe at the Methow Beaver Project. So we will be able to look at bed level changes and assess aggradation, but I'm just going to talk about sediment composition today. So this is going back to our Backy study, where we're looking at sites, 5 sites where we have before data and after data. The first slide I'm showing you here is pre-restoration data. So this is data prior to BDA installation. And we have beaver sites, BDA sites, and control sites, but none of the sites have BDAs. And this is a graph where we have sediment particle size on the x-axis and cumulative frequency on the y-axis. So as we move from left to right across the x-axis, we're accumulating bigger and bigger particles, but the cumulative frequency is going to include, right, the abundance of particles of smaller sizes as well. The 3 beaver sites that we have in this graph are all at the top for pretty much the entire graph. meaning that they have accumulated basically by the time we get to a particle with about 2 millimeter size, that's all the particles. So the entire stream bed is made up of fine particles, and that's what we would expect um, in sites with beaver impoundments. Not all of the transects that were included here were actually in an impoundment, but within these reaches with beaver activity, stream bed, as we would expect, pretty much essentially fine particles. We can see that there's a much more diverse mix of substrate at both the BDA prior to restoration, so prior to BDA installation, and their control sites. This data does not include the beaver sites, but this is post-restoration data. And in this post-restoration data, the control sites are indicated with dashed lines, and the sites with BDAs are in solid lines. This data was all collected 1 year post-restoration. So that's giving time for high flows to move sediment around. But yeah, so 1 year post-restoration. If these structures remain intact and they are currently being maintained, then we might expect these effects to continue to increase over time. However, you can see that there is now clear separation between the BDA sites and their paired control sites, and we have finer sediment distribution at the in the BDA sites compared to the control sites. So at least looking at sediment composition, we are seeing pretty clear evidence of sediment retention by these BDA structures. And I would actually note that I think the sediment retention may actually be to some degree kind of competing with or interfering with water retention because in some of these sites, like particularly Chilloust, to some degree Tunk, we would see the BDAs had retained basically so much sediment that sediment was kind of filling them up to sort of the effective BDA height. And then there wasn't a lot of potential there to then retain a water impoundment because that impoundment had kind of gotten filled up with sediment. That's one way that building a BDA structure taller, as Sawyer saw in their data, might improve the water holding capacity of the BDA structure. So I apologize that I have been talking so fast. I have to say, I talk to classes every day, and yet I almost never give webinars, and I have no idea whether, so I can't see your reactions, and so I guess I've just been plowing on ahead. But some implications. Um, Looks like BDAs in the Backy study seem to be storing sediment pretty effectively and are also slowing water compared to control unrestored reaches. However, beaver dams appear to slow and store dramatically more water than BDAs, and that would have consequences for the kind of ecosystem benefits that we would expect to see from BDA restoration compared to beaver activity. BDA construction seems to matter to water storage potential, with thicker and taller BDAs and less porous BDAs storing water more effectively than shorter, thinner, and more porous BDAs. We're still working on channel cross-section, riparian vegetation, and phosphorus transport data for the Backy study. We actually do have data on all those components post-restoration now, and still in the process of analyzing that. I would say when possible, and in many cases, this is not in any way going to be a direct competition. BDAs may be constructed in an effort to encourage beaver recolonization. I know BDA construction is likely possible in a lot of places where beaver colonization is unlikely. But I would say in this system, in this region, BDAs did not seem to be close to as effective as beaver in retaining water. And so I think conservation of beaver populations should be a priority if we're interested in retaining water in these watersheds. So I'm going to stop now, and I will be interested in folks' questions and feedback.
Thanks so much, Camille. That was fantastic. Very interesting work. I did not introduce our fellow panelist before we got started today because I knew we were running a little bit late, but I'm going to take a minute and do that now. We have Sandra Clinton and Brian Clark that are also co-panelists that are going to help handle the Q&A session. And I will, let's see if we have any questions in the chat. Or in, okay, so for our attendees, you're welcome to add questions into the Q&A session or drop them into the chat and we can answer them as they come in.
I can start us off while we wait, give people a chance to type.
Great.
So hello everyone. Sorry I was late. I was part of the slowdown of the webinar, having some technical difficulties. Thank you, Camille, for such a great talk. It is so fascinating to see all of those data around BDAs, and in particular, such a great study with the Backy design as well as comparing to beaver ponds. So my question about functionality, going back to comparing beaver ponds to BDAs, is that beavers will create lots of other secondary channels, right? And things like that. So can you comment on how effective you think BDAs are on the landscapes that you're looking at compared to beaver ponds? And, is there ways that we could add functionality that we're not currently doing in our design? That's a big question, I know.
Yeah, I mean, one of the things I know exactly what you're referring to because they build their little escape channels or maybe their feeding channels. I'm not a wildlife biologist, so beaver behavior is not my strong point here. But I see those channels and they're more prevalent at some of our sites than other sites. I would say that those are a mechanism for, water moving, further onto the floodplain. But in the places we work, there's actually a lot of topographic variation. There are also old side channels. So I feel like we could potentially, if the water table were being raised high enough, I think in terms of the ecosystem benefits and getting water into the riparian zone, I don't know how critical those built beaver channels are. I don't, if that makes sense.
Yes, I do think that makes sense. Um, I want to, let's see, do we have any questions come in yet? I can ask questions forever, as everybody on this call knows. Brian, I also want to give you a chance to ask questions. Oh, here we go. All right. How can BD, and we can also unmute people. Is that still true, Lauren? We can also unmute people if you would like to talk. I'd like to ask your question or have a conversation around it with Camille. So please just let Lauren know and she can do that. So, but we have a question from Graham Foley. How can BDAs be tuned to catch more fine sediment faster? Is it just a matter of using enough small brushy material?
So I think that is a hard question, and I definitely felt that the BDAs, honestly, in both studies, didn't necessarily ever catch enough fine sediment on their own to be self-sealing. And so that may have been one of the reasons why they remained, in many cases, remained porous. So there were some BDAs in our study that actually had packed fine sediment, like people actually, did what beavers do in our area and, scooped up sediment and put it in the dam. Um, but that wasn't possible for all the practitioners or all the locations. One of the reasons we may never have really, I feel like there's kind of two reasons why that sort of self-sealing didn't necessarily occur. One is that we were in this prolonged drought period, and so we know that these stream channels sometimes flood to a much greater degree than they did during our study period. And so there may just not have been the right flows to carry that fine sediment. In other cases, sediment clearly moved with annual flooding, and we saw that sediment coming in, as I said, and kind of filling in impoundments. But even when we got that um, sediment filling up the impoundments, it wasn't necessarily filling in the BDAs and sealing them. And I didn't have some kind of scope looking at what was going on, during those high flow events. I probably wasn't even present. Um, so I don't know exactly what was happening in terms of the flow that caused that. I would say, again, I know it's simply not always possible for a variety of reasons, but my observations would, especially in the BDA study and seeing how these things responded over time, is that I think the best way to reduce porosity is probably to do what the beaver do and actually put sediment in the dam.
Yeah, I was gonna
Um,
say, uh, I didn't look if there's anyone from, yeah, the Army, the Corps here, but one of the ways you can get away with, permitting for BDAs is because they are permeable, right? The water
yeah,
get through
exactly.
it. So it's like, let's not broadcast this too loud, whoever's on there. But yeah, I just on that, I was curious if, and this is maybe a longer term, but have if you have places where beavers have taken over the BDAs, or is there likely at any of these sites where, because
Well,
it's
that's a
essentially would be a
really good
measure of how much
question.
better they are at packing the dams than we are, because they're sealed behind my house, solid.
Ab Absolutely. And they maintain them. I mean, there's also the last time we were out collecting data at high flow conditions, um, there was water going around the BDA. The water level had come up enough. It was over the floodplain, and there was significant flow around the BDA. And in that stream had a beaver reach on the same stream, and the beaver had raised their dam. So they had built their dam higher to catch that spring flow, but people can't respond that quickly. Um, there is actually in this study no to beavers taking over BDAs, but one of our study sites has been infiltrated by beaver, and they've built their own dams that partially overlap with the BDA reach, which was super fun to work around, but otherwise, no. And in fact, there's been a net loss of beaver from, sites that we're aware of in at least two cases one case we know they were trapped for infrastructure protection reasons, and in another place, very likely they were trapped by hunters. So,
Cool. Thanks.
I have a question. I'm wondering, it sounded like at the end of your kind of takeaway section on that last slide, you had mentioned that bigger, like taller and like larger BDAs seem to be performing better. In that vein, is there an optimal size that practitioners should be looking for to encourage that functionality with BDA construction?
I mean, we didn't really see a leveling off, and I think I went through the slides so fast that it might not have been clear, but in Sawyer's data, the thickness, when we said that the thicker BDAs had better water retention, that was actually like not the width of the stream, but the thickness of the dam from like upstream to downstream, if that makes sense, which is logical. Um, One of our practitioners, who's actually a hydrologic engineer, had these incredibly thick dams that were like had 3 rows of posts and were just like absolutely packed full of material. And they did a great job actually of retaining water. That was some of our longest hydraulic residence times. So
So I'll jump
I
in
was
with another. Oh, go ahead.
maybe
Go
this.
ahead, Brian.
Oh yeah, I think you have to. I know you have to go, but I was gonna say. I mean, it makes sense to me that the larger, thicker ones are gonna have the longest hydraulic residence time. Did you look at what about? I mean, most of the time you put in many of these and closer together. It's a complex of them in terms of
yeah,
is right. The one or two go, who cares? That's not really the point of the project. Is to get them all.
right.
Um, yeah. Did you see something with? Sorry, I think maybe I missed the map. If you already said this, but
No, that's
how
okay.
close they are, how many there are, spread out.
Yeah, so for residence time and volume, pool volume, those were measured on individual impoundments. So that's like behind a single dam, whether it's a BDA or a beaver dam. All of these were in complexes, and depending on the project, there may have been 5 to more like a dozen within a reach where we measured travel time. Um, and I would have to say, in this data set, I don't know if there was a huge amount of consistency with, say, within the study reach, there were 5, just within the study reach, there were, 15 in terms of how much they were slowing water. And I think that's because the characteristics of the dams in terms of things like height, thickness, porosity just varied a lot. But yeah, you would expect more would be better. So.
Cool, thanks.
Mhm.
So
So you
apologies.
asked us to let you go, so I should stop there.
That's okay. I mean, it'll be okay if I can go in like the next 3 to 4 minutes.
Okay, I'm done. Sandra, I'll let you wrap it up. I'll stop talking.
This is Brian and I all the time.
Yeah.
I'm sorry if I missed it earlier, Camille, if you mentioned it when I was trying to get on. Are you doing any groundwater surface water interaction measures, whether putting in piezometers and measuring head or anything around the BDAs versus the beaver ponds?
So this is something we didn't include because this is something that the Methow Beaver project was doing as part of their work. I do not know the status of that data, however. I mean, it would be great if we could incorporate that data because they are, definitely co-authors on this project, but I don't currently have access to it. But yeah.
We'll just have to get them out to give a follow-up webinar on the other data.
Yeah.
Do we have other people who would like to type in questions or ask a question of Camille as we approach the end of the hour? Are people a chance?
Oh, Sandra, maybe it's before you hopped on, we said we would try and let Camille go a little early to teach a class.
Oh, yes, that's important. I did wear my project shirt. I just wanted to say that to
I saw
everybody.
that. Well, thank you guys for having me, and I'm sorry if I talk too fast. And please feel free to follow up with an email to me, and I'd be happy to. Yeah, I'd happy to talk to you about our work. Send you any data if it's in a reasonably finalized form. So, thanks again.
Fantastic. Thank you so much for your time today and good luck with your class. I'm going to
Okay.
drop your email into the chat so that everyone can contact you. And then I will just say stay tuned to our next speaker series. We'll be announcing all of that through our newsletter or through our social media channels. And you can also find a link to that information on our website with the Beaver Institute for those who are following along and interested in continuing to listen to our speaker series. We will have another one next month. And with that, I'll just thank everybody for being here and spending the time with us, and we'll catch you next time. Thanks, everybody.
Thanks, Camille, for presenting today.